Before we begin, take a moment to get comfortable. Let your arms go heavy, your breath slow. And as you listen, feel free to leave a comment sharing what time it is, where you are, and what city or village you're listening from. It's love to know. And if you'd like more quiet stories like this one, don't forget to subscribe so they gently appear when you need them most. Now, let's begin. Far above the surface of the earth, a cold, ancient sphere quietly drifts through the sky. It reflects no light of its own, only what it borrows from the sun. The moon has no atmosphere, no wind, no sound, and yet its influence reaches across nearly 400,000 kilometers, culling gently on the surface of our world. What it pulls is not rock, not air, but water. And not just the oceans, but even the smallest lakes and deepest crusts. In this quiet interaction, the moon reminds us of something fundamental, that gravity is not loud. It does not shout. It does not force. It simply pulls, endlessly, softly. The tides of Earth begin here, with this unseen force, so small we barely notice it, but so persistent, it moves entire oceans. To understand tides, we must begin with the truth that feels too slow to notice. The Earth is turning constantly, and as it turns, it spins beneath the gravitational influence of the moon. This combination, the moon's gravitational pull and Earth's rotation, is what gives us high tide and low tide, and the quiet rhythm of water that coastal cities have obeyed for centuries. But what is gravity, really? Gravity is a force between two masses. It is proportional to the size of each mass and inversely proportional to the square of the distance between them. This was described first by Newton and later refined by Einstein. The moon pulls on the Earth, yes, but more specifically, it pulls on different parts of the Earth with different strengths. The part of the Earth that is closest to the moon experiences a stronger pull. The far side, less so. It's different. This gravitational gradient is what stretches the water. It creates a bulge of ocean on the side facing the moon, and another on the side facing away. This is why there are two high tides every day. One, when your part of the Earth is directly under the moon, and one when it is directly opposite. It is not the moon dragging oceans across the planet. Instead, the Earth is rotating through these bulges of water. And yet, this explanation, while mathematically sound, still feels incomplete. Because when you stand at the edge of the ocean and see the tide roll in, it doesn't feel like a cosmic equation. It feels like breath, like the planet itself is slowly inhaling and exhaling. There are many layers to this motion. The Earth does not simply orbit the sun. The moon does not simply orbit the Earth. They both orbit a shared center of mass, called the barycenter. It lies about 4,600 kilometers from Earth's center, still within the Earth, but not at its center. This mutual orbit causes both the Earth and moon to wobble slightly. This wobble, combined with Earth's rotation in the moon's elliptical orbit, adds complexity to the tidal cycle. That's why not every high tide is the same height. That's why tides shift slightly each day. And that's why sailors, fishermen, and coastal dwellers have studied tidal charts for generations, because they change, and they matter. The oceans do not respond instantly to the moon. There is a lag, a delay, due to the inertia of water and the friction of coastlines. This delay creates what is called a tidal lag, causing high tides to occur after the moon is directly overhead. It is not unlike pulling on thick syrup with a spoon. The pull is immediate. The motion is delayed. This delay also means the tidal bulge is not perfectly aligned with the moon. Instead, it is slightly ahead of it. That has another consequence. The moon is being gently pulled forward in its orbit, causing it to slowly drift farther away from the Earth, roughly 3.8 centimeters each year. Quietly, gradually, the tides, then, are not just a result of the moon. They are also a force acting back on it. The Earth is losing energy. The Moon is gaining momentum. The days on Earth are slowly getting longer. Not by minutes, just milliseconds. But the trend continues. In this way, the tides are not static. They are part of a long, slow exchange of energy, an ancient conversation between two celestial bodies. Neither speaks, but both respond. And while the moon is the primary driver, it is not alone. The sun also exerts a gravitational pull on the Earth, and when the sun and moon align during full moons and new moons, their combined pull creates spring tides. These are the highest high tides and the lowest low tides, not named for the season, but for the way the water springs higher. Conversely, when the sun and moon are at right angles during quarter moons, they create neap tides, where the difference between high and low tides is minimized. It is a quiet dance of gravity, a tug of war played out over oceans. Yet all of this remains invisible to the eye. The forces involved are never seen, only felt. Felt in the erosion of cliffs, in the arrival of ships, in the shifting sands of coastal estuaries, in the spawning patterns of marine life that rely on the turning of the tide. Like a cosmic clock, if you were to drift above the Earth and watch the oceans from space, you would see tides not as waves, but as great, subtle bulges circling the globe with the moon's pull, endlessly reshaped by land masses and underwater ridges. Some coastlines feel the tides deeply rising and falling by meters each day. Others feel only gentle lapping. It all depends on geography, on the width of the continental shelf, on the shape of the bay, on the slope of the seabed beneath. Tides are amplified in funnel-shaped bays. In places like the Bay of Fundy in Canada, the tide can rise over 15 meters, a dramatic reminder of what invisible forces can do when geography cooperates. And tides are not just for the sea. They exist in the Earth's crust and atmosphere, too. These are called earth tides and atmospheric tides, subtle shifts caused by the same lunar pull, just less visible. Your body even feels it, though the effect is too small to notice. It's strange then to realize that something as large as the ocean can be shaped by something as quiet as the moon, not by touching it, not by commanding it, just by being there. Pulling dot in the next section, we'll explore the biology of tides, how marine animals timed their lives to lunar cycles, and how ancient humans may have followed the same rhythms without even knowing why. The tide is not just emotional water. It is a signal, one that has echoed across billions of years, shaped life from the very beginning, long before humans watched the water rise and fall, before the first sails were ever hoisted, even before there were continents as we know them. The oceans pulsed with the rhythm of the moon in the shallows of ancient seas. Tiny organisms evolved not only to survive, but to time their lives with these celestial shifts. And over eons, this synchronized rhythm became embedded into the biology of life. In the intertidal zones, the regions between high tide and low species are still governed by this lunar metronome. Crabs scuttle across exposed rocks during low tide, then retreat as the waters rise. Barnacles, clinging like stone to stone, open only when the sea returns. Mussels anchor themselves in thick clusters, their shells opening and closing with the tides. Some fish, like the elusive grunion, even spawn on land, timing their leap onto sandy beaches with the highest tides of the lunar cycle. Their eggs incubate in the sand, untouched by predators, until the next wave of spring tides washes them back to sea. A delicate gamble, one that depends entirely on knowing the moon. Coral reefs, too, pulse with the calendar of tides. Many species of coral reproduce through mass spawning, releasing eggs and sperm into the water simultaneously on specific nights tied to the lunar cycle. The water becomes clouded with life, a reproductive symphony orchestrated by the moon. It is not simply day and night that creatures watch, but the phase of the moon, the height of the tide, the quiet pull of gravity they cannot see, but somehow sensed on in some marine worms. Lunar cycles affect the very structure of their DNA, altering how genes are expressed depending on whether the moon is full or dark. These are not myths. They are observable, repeatable facts. Biology, obeying physics, and humans, though we live further from the shore, are not separate from this rhythm. Long before we had calendars, early societies watched the tides to mark time. Fishermen knew when the catch would be plenty. Coastal farmers planted with the knowledge that certain tides would flood and nourish their soil. In Mesopotamia, in Greece, in Polynesia, ancient cultures built their life around the tide tables, some without writing, without telescopes, just observation, just intuition. In medieval Europe, tide mills were constructed, early water mills, powered not by rivers, but by the inrush and outflow of tidal waters. The very force that moved ships was now turning stones, grinding grain. And then there were the moon maps, scratchings in bone, stones marked with holes, not decorations, but cycles. Some archaeologists believe these were lunar calendars used to track both the moon, K, and the tides. Even today, with satellite forecasts and atomic clocks, fishermen, surfers, K, and ocean scientists still rely on the tide. Harbors still dredge their floors based on the pull of the moon. Shipping companies calculate fuel and weight based on the tide chart. And then there is our own biology. The average adult human is 60% water. Does the moon affect us? The tides within the human body are tiny. It's too small to measure. But our circadian rhythms, our internal clocks, do respond to light and gravity. Recent studies suggest that our sleep patterns may shift slightly during different phases of the moon. On full moons, some people sleep less. On new moons, slightly deeper. It is not dramatic, but it is there. And then there's the myth of the lunar lunacy, the idea that the full moon causes madness. It is mostly folklore, but it persists, likely because people seek patterns. And the moon is an easy one to watch, even in language. K. The moon lingers, lunatic, moonstruck, tidal wave. But tidal waves, the real ones, are not caused by the moon. They are caused by earthquakes. The proper term for those is tsunami, tides. By contrast, are regular, predictable, K, and long in wavelength. This predictability has allowed humanity to use tides for energy. Modern tidal power stations exist in places like France, South Korea, and Canada, where tidal flows are strong and consistent. Okay. Water is channeled through turbines, generating electricity from the moon's pool. It is clean, renewable, and ancient tidal energy is not without limits. It requires specific geography. It can affect marine life. But it reminds us, the moon is not just a passive observer. It is an engine, a quiet one, and like all engines, it has moving parts. The moon is drifting away, as we've mentioned, slowly, gently, but steadily. Okay. And as it does, the tides on Earth will weaken. In millions of years, they will be smaller, more gentle. Eventually, the Earth and Moon will become tidally locked, each showing only one face to the other. No more shifting. Tides, just stillness. But that's far in the future. For now, the moon continues to shape our world. Its gravitational reach even affects satellites, causing tiny shifts in orbits, minute variations in GPS signals, even subtle adjustments in timekeeping for astronomical observations. Time and tide, after all, are deeply linked. The moon's rhythm became part of our own. From the migration of sea turtles to the resting cycles of humans, the gravitational dance of two celestial bodies has left its imprint in flesh, stone, and memory. To stand on a shore and watch the tide come in is not simply to watch water move. It is to witness an ancient interaction between body and body, mass and mass, invisible and ever-present. The moon may seem distant, but it is always with us, pulling, guiding, never touching, but never letting go. The moon's pull is not uniform across the earth. This is the foundation of tides, because the earth is a sphere, a rotating one. Different parts of the planet are at different distances from the moon at any given moment. At the point directly facing the moon, its gravitational pull is strongest. The water there is drawn slightly toward the moon, creating what we see as the high tide. But interestingly, on the opposite side of the earth, the side farthest from the moon, there is also a high tide. Why? It's not because the moon is pulling the water from that side. Quite the opposite. The moon pulls more strongly on the Earth's center than it does on the far side. So, the Earth itself is being pulled slightly more than the water on the far side, causing that water to lag behind, forming another bulge. It's a subtle shift, visible if you were watching from space in real time, but over hours, it becomes the tide. This means, at any given time, there are two high tides on Earth, one on the side closest to the moon, and one on the side farthest from it. As the Earth rotates, any given location passes through both of these bulges in a 24-hour period, giving most coastal areas to high tides and two low tides every day. But it isn't always that neat. The sun also plays a role in tides, not as strong as the moon's, but significant. When the sun and moon align during full moons and new moons, their gravitational pulls combine. This produces what are called spring tides, higher high tides, and lower low tides. Despite the name, spring tides have nothing to do with the season. They come from the old Anglo-Saxon word springdon, meaning to rise or to swell, the T. Then, during the first and third quarters of the moon, when the sun and moon are at right angles relative to the Earth, their gravitational forces partially cancel out. This results in neap tides, tides that are less extreme, with smaller differences between high and low. So the tide chart is not a flat rhythm. It is a layered symphony. Lunar pull, solar influence, planetary rotation. They all intersect in a predictable but richly complex pattern, and local geography matters too. If the coastline is narrow and steep, like a fjord, tides can surge dramatically. If it's shallow and wide, like a flat bay, the tidal change may be barely noticeable. Some places, like the Bay of Fundy in Canada, experience tidal ranges of over 15 meters, 50 feet between low and high tide. Elsewhere, in parts of the Mediterranean or the Gulf of Mexico, tides may change by only a few centimeters. Ocean depth, continental shelf shape, underwater topography, all of these change how the ocean responds to the moon's pull. This local variation also gives rise to tidal currents, horizontal movements of water caused by the rising and falling tide. These currents can be strong, especially in narrow channels or straits, and are different from the larger scale ocean currents, like the Gulf Stream, which are driven by wind and temperature differences. Tidal currents affect navigation, erosion, and even marine ecosystems. In estuaries, where rivers meet the sea, tides can push salt water upriver and pull it back again, creating brackish habitats rich in biodiversity. These zones are nurseries for many marine species. Fish spawn there, birds feed, and cadias route themselves against the push and pull. Without the tide, these ecosystems would collapse, even on land. Tides influence life. Seaweed clings to rocks, adapting to be submerged and exposed in cycles. Insects, amphibians, and reptiles that dwell near coasts time their activities with the tides, advance, and retreat. The moon shapes not just the oceans, but the entire coastal biosphere. And then there's timing. Tides do not follow the standard 24-hour clock. Instead, the cycle is closer to 24 hours and 50 minutes because the moon is moving to dot each day. The moon rises about 50 minutes later than the day before, so high tide comes about 50 minutes later as well. This explains why tidal calendars and clocks must account for the moon's motion, not just Earth's. Ancient navigators knew this intuitively. They could tell from the moon's phase and position what the tide would be. No need for digital apps, just observation. In many indigenous traditions, this lunar awareness was passed down through stories and rituals. Some Pacific Island cultures measured time not in days or hours, but in tides and moon cycles. Their knowledge of the ocean, including the tides, allowed them to navigate vast distances in open canoes, using only the stars, swells, and sky dot. And now, as science advances, we return to this ancient intuition with deeper tools. Tide predicting machines, first built in the 19th century, used gears and levers to model the lunar and solar effects mathematically. These analog computers were marvels of precision, capable of predicting tides years in advance without electricity. Today, satellites like Topex, Poseidon, and Jason 3 map seas surface heights globally, tracking tides with centimeter-level precision. We know not only what the tide is, but what it will be decades from now. And yet, there is still something mysterious about the tide. Perhaps it's the sound, the slow hush of the incoming wave, or the feel, sand shifting beneath your feet as water pulls away, or the sight of a harbor that empties and refills like a breath. The tide is the earth breathing in rhythm with the moon, and we are part of that breath. Even when we cannot see the moon, we can feel it in every wave, every shore, every quiet coastal night, and just as the moon shapes the ocean, so, too, does it shape our imagination. From poetry to science, the moon has inspired wonder because it reminds us that something so far can have such a deep effect. The science of tides is a science of connection. A pull, a rise, a fall, predictable, calculable, and yet always poetic. And in that gentle motion, in that quiet force, lies a truth. The universe speaks not only in light and stars, but in water, and it is listening. Before we begin, tell me, what time is it where you are? Where in the world are you listening from? Leave it gently in the comments, and if you find this soothing, subscribe for more.com immersive science every week. Now, let's return to the tide. We've explored how the moon's gravity pulls at Earth's oceans, creating the tides. But tides are not simply vertical shifts. They also flow sideways across the globe in grand ocean-sized loops, known as amphidromic systems. An amphidromic point is a spot in the ocean where the tide doesn't rise or fall at all. Around this center, tides rotate in vast spirals, like hands on a cosmic clock. In the northern hemisphere, they turn counterclockwise. In the southern hemisphere, clockwise. It's all due to the Coriolis effect, a result of Earth's rotation. These tidal systems aren't something we see with the naked eye, not like waves or ripples. But if you tracked the high tides over time in places like the North Sea, the Gulf of Mexico, or the Indian Ocean, you'd notice the tide rotates around these invisible centers. Water flowing not just in and out, but around, in slow, majestic circles. It's a reminder. Gravity may pull in straight lines, but Earth's spin introduces a twist, and so, as the moon moves in its orbit and Earth spins beneath it, these spiraling patterns create subtle differences in tide times from one place to the next. In London, the Thames rises dramatically twice a day. But in Tahiti, just 1 week tide might come and go in 24 hours. Some places have diurnal tides, 1 cycle per day. Others have semi-diurnal tides, 2 cycles. And some have mixed tides, where the 2 high tides are unequal in height. This local variation is more than a scientific curiosity. It affects the lives of millions. Harbor masters must plan docking schedules around these shifts. Ferry services adjust routes and times based on expected tide height. Construction projects, from bridges to seawalls, have to account for not just present tides, but future changes caused by rising seas. Even search and rescue operations rely on tidal predictions to estimate where currents may have carried missing persons or lost cargo. 1 hour can make the difference between finding a stranded vessel or missing it entirely. And for island nations, especially low-lying ones, tides are more than background noise. They're existential. As sea levels rise, high tides now reach farther inland. What was once a harmless lapping at the shore becomes nuisance flooding, regularly washing over roads, homes, and farmland. When the sun, moon, and earth align during king tides, these floods grow worse. In places like Tuvalu, Kiribati, and parts of Bangladesh, families now move with the moon, not in wonder, but in retreat. Salt water creeps into wells, crops wither, and the ancient rhythm of tide becomes a quiet threat. And yet, paradoxically, tides also offer a solution, a renewable one. Tidal power is emerging as a key part of future clean energy portfolios. Unlike wind and solar, which can be unpredictable, tides follow a known pattern. We can calculate them centuries in advance. Tidal barrages, like the Lorraine plant in France, trap seawater at high tide, then release it through turbines as the tide recedes. Underwater turbines, known as tidal stream generators, spin like windmills, powered by strong tidal currents in places like Scotland's Pentland Firth. These installations, though expensive, hold promise for coastal communities. If built with care, they generate energy without carbon and with minimal impact on wildlife. Some engineers are even experimenting with floating tidal platforms, which can be moved into position and removed without damaging the seabed. Science flowing with nature, not against it, but there's a delicate balance. Tides sustain ecosystems as much as they can power grids. Salt marshes, for example, rely on tidal flushing to deliver nutrients, remove waste, and maintain salinity. These wetlands act as nurseries for fish, buffers against storms, and filters for pollution. Block the tide too much, and you risk collapse. That's why modern tidal engineering involves not just physicists and architects, but marine biologists, ecologists, and local communities. It's not just about water moving. It's about understanding what that motion means for life. Let's turn now to another mystery of the tides. Why does the ocean respond to the moon's gravity, but not a glass of water? You may have heard this question before, or even wondered yourself. After all, the moon's pull is everywhere. Shouldn't your bathwater shift toward it? Shouldn't a cup of tea show a tiny tide? Technically, yes, but the effect is minuscule. Tidal forces depend on differential gravity, the difference in gravitational pull between one side of an object and the other. The Earth is large enough that the moon's gravity pulls more strongly on the side nearest to it and less on the far side, creating that bulge in the oceans. But for a cup of tea, the difference in pull from one side of the cup to the other is unimaginably small, far too tiny to notice, far smaller than thermal motion or air vibration or even the slight jostle of your hand. The same applies to lakes. Despite their size, many lakes show only barely measurable tides, often a few millimeters, because they lack the scale, the depth, and the open connection to the ocean that lets the tide really breathe. And so, the ocean responds, not because it's made of water, but because it's large enough to notice. It's also fluid enough to move. And this brings us to yet another subtle effect of tide's tidal friction. You see, as the moon pulls at the oceans and the earth rotates, the ocean doesn't flow instantly toward the moon. It lags behind, slowed by the friction between water and land. This lag means the bulge is slightly ahead of the line connecting Earth and Moon, and this bulge pulls back on the moon. Yes, the moon pulls the oceans, but the oceans pull back. This gravitational feedback slows Earth's rotation by about 1.7 milliseconds per century and causes the moon to move farther away by about 3.8 centimeters per year. These are tiny numbers, but over millions of years, they change everything. Hundreds of millions of years ago, a day on Earth was only 22 hours long. Tides were more extreme. The moon was closer, looming larger in the sky, a constant force, quietly changing the rhythm of Earth's spin. In millions of years in the future, the moon will drift so far that total solar eclipses will no longer occur. It will appear smaller in the sky. The tide will weaken our clocks, our calendars, our days and nights. All of them bear the imprint of this interaction. We are, in a very real sense, spinning slower because of the moon. And still, it continues. Each night, it rises. Each day, the tide obeys. Each generation, humans return to the shore and watch, some for science, some for beauty, some because the waves tell a story they cannot quite name. But deep down, we all feel it. We are not separate from the cosmos. We are moved by it, pulled by it, lifted, even slightly, by gravity older than bones. A child playing in a tide pool, a heron lifting its wings as the tide returns, a boat rising softly on its moorings. All of it because of the moon, because water remembers, because the sea listens. Far beneath the surface, where sunlight fades and pressure builds, the tidal pulse continues. It might seem that tides are a surface phenomenon, the rising and falling of the sea against sandy shores, the slow encroachment up river mouths, the lapping at coastal rocks. But in truth, tidal motion extends downward, touching even the abyssal plains of the ocean floor in the deep sea. Where the water remains cold and dark, the tides create slow, sweeping internal waves. These aren't the crashing whitecaps of stormy surf. Instead, they are vast undulations in layers of differing temperature and salinity, rippling silently through the water column. When these internal tides encounter underwater mountains, ridges, or continental slopes, they break just like waves on a beach, mixing nutrients upward from the depths into shallower layers. This quiet, vertical motion nourishes plankton near the surface, creating entire food webs. In this way, the moon's pull helps to sustain oceanic life at all levels, not by spotlight, but by stirring the darkness. One could think of the oceans not just as moving back and forth, but as breathing, a global inhalation and exhalation, orchestrated by gravity, shaped by the land, and balanced by heat. Wherever there is water and time, the moon leaves its mark. Even landlocked bodies of water, like the Mediterranean or the Black Sea, experience subtle tidal shifts. Although they are enclosed, they still connect through narrow straits or subterranean flows to the larger rhythm of global oceans. Yet the tide doesn't just obey the moon. The sun, too, plays a role, though it's much farther away. The sun, it's enormous. Its gravitational influence on Earth is nearly half as strong as the moon's when it comes to tides. And when the sun, Earth, and moon align during new and full moons, their combined pull creates what we call spring tides. Despite the name, spring tides have nothing to do with the season. The term comes from an Old English word, springen, meaning to rise. During these alignments, the high tides are higher, the lows are lower. Coastlines stretch further in both directions. 2 weeks later, when the moon is at first or third quarter at a right angle to the Earth's sunline, we get neap tides. These are the quiet tides, the ones with the least variation, still present, still predictable, but softened by cosmic geometry. And so the rhythm of the sea follows a 2-week pulse, swelling, receding, swelling again. Ancient humans knew this well. Long before telescopes, satellites, or tide gauges, coastal communities observed these patterns. They could feel the connection between the moon's shape in the sky and the behavior of the ocean at their feet. Lunar calendars were not mystical inventions. They were tools for survival in parts of the world where the sea retreats for miles. During low tide, such as in the Bay of Fundy or the Severn Estuary, entire fisheries, salt pans, and footpaths were designed around this rhythm. People timed their work not by clocks, but by the moon. In Polynesia, navigators used an intimate understanding of ocean swell and tide to voyage across open seas long before Western maps were drawn. They knew that certain wave patterns revealed distant islands, and that tides could alter the timing of safe passage through coral reefs. Even today, satellite data, GPS, and predictive models are informed by centuries of empirical knowledge passed through coastal generations. Because while our instruments may now be digital, the tide remains analog, steady, graceful, and curved like the moon itself. And so it goes, tide after tide, day after day. But what happens when a tide meets resistance? Consider a river that flows into the ocean in places like the Amazon, the Ganges, or the Bay of Fundy. The incoming tide is so strong that it pushes upriver, creating tidal bores. These are surging waves that move against the river's current, sometimes traveling dozens of miles inland. They can be several feet high, loud, and forceful, like a liquid wall in some regions. Surfers ride these bores for minutes at a time, gliding upstream through jungle-fringed watercourses. But for local ecosystems, these bores serve another purpose. They carry salty nutrients far inland, feeding estuarine systems and helping to balance the mixture of fresh and salt water that certain species need to survive. Tides do not respect boundaries, not of rivers, lands, or nations. They move according to mass, motion, and alignment. Always have, always will. And that brings us to an even more fascinating, slower rhythm, the lunar nodal cycle. The moon doesn't orbit Earth in a perfect circle, and its path isn't perfectly aligned with Earth's equator. Instead, its orbit tilts about 5 degrees relative to our orbital plane. And this tilt slowly rotates, or precesses. Over 18.6 years, this wobble means that the moon's pull on Earth and on Earth's oceans also wobbles every 18.6 years. Tidal ranges increase and then decrease in a predictable way during the maximum phase. High tides are higher, low tides are lower. In the minimum phase, the differences are less pronounced. This cycle affects not only tides, but also the long-term planning of flood defenses, coastal engineering, and climate modeling. Urban planners in coastal cities must now consider where the nodal cycle will be in relation to expected sea level rise. A major storm hitting at high tide during a nodal maximum may cause far more damage than one hitting during a nodal low. We tend to think of tides as daily or monthly phenomena, but their deeper rhythm spans decades. And this rhythm is not just physical, it's biological too. Many marine animals synchronize reproduction with the tides and the moon. Corals in tropical seas release their gametes in mass spawning events timed with full moons and specific tides. Horseshoe crabs come ashore during spring tides to lay eggs, their ancient bodies glittering beneath the moon. Grunion, small silvery fish found along the Pacific coast of the Americas, beach themselves during particular nighttime tides to spawn. Their behavior is so precisely timed that entire species migrations happen in coordination with lunar gravitational cycles. Even humans, it turns out, may not be entirely immune to the moon's rhythm. While scientific evidence for a strong lunar influence on sleep or behavior is mixed, some studies suggest slight correlations between lunar phases and human circadian patterns, especially in sleep quality. Perhaps it's a biological memory, deep within our evolution of when life first emerged from tide pools and shallow coastal waters. The moon has always been part of that story. It is the reason Earth has tides. Yes, but also the reason Earth has relative climate stability. Without the moon's gravitational influence, Earth's axial tilt would wobble wildly over time, destabilizing climate, seasons, and even the evolution of life itself. Instead, the moon acts as a celestial anchor, holding Earth's orientation steady, letting the tide rise and fall with quiet predictability. In every wave, in every drop of seawater, in every rise and fall of the tide, we see the result of billions of years of gravitational partnership. The Earth spins, the moon orbits, the water moves, and life listens. Somewhere, right now, the tide is turning. Not because of storms or winds or distant ships, but because the moon passed overhead and gently tugged at the sea's edge, as it has always done. Not loudly, not quickly, but with the patience of the cosmos. The beach feels it. The mangroves feel it. The sea turtles feel it, okay? And we, if we slow down enough, feel it too. Further out to sea. The power of the tides is not only found in the water's movement, but also in the steady, planetary logic that guides it, a force so ancient that it predates all human history and outlasts our civilizations. The moon pulls, and Earth responds. No negotiation, no decision, only gravity, inertia, okay, and time. But let's shift our gaze from the surface of the water to the vast machinery beneath the deep ocean basins, okay, trenches and ridges. It is here, in the darkest places, that the tidal energy becomes something more than a gentle rise and fall. It becomes work. Tidal forces generate friction as ocean water brushes against the seabed. This friction converts some of the tidal energy into heat, not enough to warm the ocean in any dramatic way, but enough to have consequences over millions of years. Over time, this tiny loss of energy results in one of the most remarkable long-term effects of tides, the gradual slowing of Earth's rotation. That's right. The length of our days is increasing, slowly but surely. Hundreds of millions of years ago, a day on Earth was only about 21 hours long. As the moon continues to siphon off angular momentum from Earth via tidal friction, Earth's spin slows down, and the days grow longer by about 1.7 milliseconds per century. It is such a tiny amount that we can't perceive it in our lifetime. But in the silent ticking of geological time, it matters. Meanwhile, as Earth slows down, the moon moves away, inch by inch, year by year. Currently, the moon is drifting farther from us at a rate of about 3.8 centimeters per year. It does this to conserve angular momentum in the Earth-Moon system. In cosmic terms, it's like a dancer spinning with arms outstretched. As she draws her arms in, she spins faster. As she extends them, she slows down. Earth and Moon perform this dance together. Eventually, billions of years from now, Earth and the Moon will reach a kind of gravitational equilibrium known as tidal locking. In this scenario, the Moon will no longer move away, and Earth will rotate once for every orbit of the Moon. One side of Earth would always face the Moon, just as one side of the Moon always faces Earth. But long before that happens, our sun will swell into a red giant and change the story completely. So for now, we live in a delicate moment of balance. Even this balance influences our technology. Modern tidal prediction isn't just about sailors and fishermen anymore. Today, we use tidal models to calibrate satellite data, correct global positioning, systems, and model climate interactions between oceans and atmosphere. Understanding the moon's effect on water helps us understand the entire Earth system, from weather to sea level rise to renewable energy planning. In places like the coast of France, Canada, and the United Kingdom, tidal power stations already harness the kinetic energy of the tides to produce electricity, a clean, predictable source of energy drawn directly from lunar gravity. And this predictability is key. Unlike wind or sunlight, tides can be forecast centuries in advance with precision. Okay, the moon's orbit is stable, its pull reliable, in a world filled with chaotic weather patterns and shifting climate systems. The tide is a constant, a metronome keeping cosmic time. But even as we focus on these grand global systems, the tide continues to shape life in the smallest, quietest corners. On a rocky coastline at low tide, you might find tide pools, little pockets of seawater trapped between stones. In these microhabitats, tiny creatures endure cycles of submersion and exposure, warmth and cold saltiness and dilution. Anemones, sea stars, limpets, and hermit crabs move between these changing worlds, adapting over millions of years to the push and pull of the sea. Tidal life is not static. It is rhythmic, responsive, and resilient. Further inland, the estuaries, where rivers meet the sea, serve as nurseries for marine life. These brackish zones are shaped by tides too. The timing of the tide determines when young fish can move into safer shallows, when nutrients are flushed in from the ocean, and when sediment is stirred and resettled. Tides sculpt shorelines, shift sands, can create marshes, and with the rising and falling of sea levels due to climate change, understanding these tidal dynamics becomes more critical than ever. Sea level rise doesn't just add water, it changes the timing, height, and inland reach of the tides. What was once a high tide may become a regular tide. What was once a rare flood might become routine. Scientists, engineers, and policymakers now factor tidal data into coastal defenses, urban planning, and conservation strategies, predicting future tides and how they will change with melting ice and warming oceans. Is no longer an academic pursuit. It's a matter of safety and sustainability. And yet, for most people, the tide remains something you notice at the beach. It's a gentle surprise water where there was once sand. It's a slow disappearance of a sandcastle, the retreat of a footprint. We rarely think about the immense scale and power behind it, the gravitational pull that moves oceans also affects the land beneath our feet. Yes, Earth's crust flexes slightly in response to lunar gravity, something called earth tides or solid earth tides. These are tiny vertical movements in the planet's surface. It's typically only a few centimeters in range, but measurable with modern geodetic instruments. Even the atmosphere feels the moon's pull, leading to atmospheric tides, subtle oscillations in pressure and density that influence weather patterns in small but detectable ways. In every layer of ocean, land, air, the moon tugs. This unseen choreography binds us to the cosmos every moment of every day. As you breathe, walk, sleep, or simply sit still, the moon is pulling at your world. It is lifting the seas, stretching the earth, shifting the air. And yet, it does this so slowly, so quietly, that we forget it's even happening. We think of gravity as a force that pulls things down. But here, gravity is not down, it is through. It moves through the earth, across the oceans, through your body. It binds the moon to the earth and the earth to the sun, and the entire solar system into one balanced motion. The tides are simply the visible edge of that connection, a gentle, rising echo of the invisible. And in that rising, there is comfort, because no matter how chaotic the world may seem, the tide still comes in. The tide still goes out. The moon still moves in its path. And the ocean, patient and vast, responds. Right now, somewhere on Earth, water is rising. Somewhere else, it is falling. And in both places, life moves quietly with it, floating, feeding, breathing. The moon does not hurry. It does not shout. It does not rush the sea. It simply pulls. And the ocean answers. The tides continue their patient work, rising and falling in great arcs that wrap around the planet like a slow, silent breath. But beneath the gentle rhythm lies a world of intricate physics, patterns built not only by the moon, but shaped by the complex geometry of Earth's oceans, coastlines, and the rotation of the planet itself. To understand the full picture, we have to look beyond just the moon's gravity. We must also consider how that gravity interacts with the Earth's spin as Earth rotates on its axis. It carries the ocean with it, but this rotation isn't perfectly aligned with the tidal bulges created by the moon's gravitational pull. Instead, the rotation slightly drags those bulges ahead of the moon's position. This offset is not a mistake in nature. It's a fundamental part of the dance. That small lag causes something extraordinary. It exerts a gravitational pull, pank on the moon, a kind of tug of war between the Earth's oceans and the moon's path. Over time, this slows Earth's rotation and, as previously mentioned, pushes the moon gradually farther away. This quiet mechanism, invisible to the eye, reveals how tides aren't just about water. They are a conversation between two worlds, written in the language of gravity and time. But that conversation becomes even more intricate, when you realize the ocean isn't one single body of water. It's many: the Atlantic, Pacific, Indian, Arctic, and Southern, each with their own basins, ridges, and underwater landforms. Each with coastlines that bend and twist the incoming tides into complicated patterns of highs, lows, surges, and stillness in narrow bays. The tide can become amplified, funneled into higher peaks than in the open sea. This is known as tidal resonance. In places like the Bay of Fundy in Canada, this effect produces some of the highest tides in the world, sometimes reaching over 16 meters, more than 50 feet. Here, the moon's influence is sculpted by local geography. The timing of the tide matches the natural period of the bay's oscillation, like pushing a child on a swing at just the right moment, over and over. With each cycle, the water is pushed a bit farther, a bit higher, and yet it's just a short distance away in less dramatic inlets or straighter coastlines. The tidal difference might be barely noticeable, a quiet lift, just a few centimeters, easily missed by the casual observer. This variation is why no two beaches experience the tide in exactly the same way. Even time itself gets folded into its complexity. While a day lasts 24 hours, the tidal cycle is closer to 24 hours and 50 minutes. This is because the moon is also orbiting Earth in the same direction that Earth spins. By the time Earth has made a full rotation, the moon has moved slightly along its orbit, and it takes an extra 50 minutes for the same tidal bulge to realign. Beneath it, this is why high tide occurs roughly 50 minutes later each day. It's not a fixed schedule. It's a slow drift, dependable, but never exactly the same in many parts of the world. This results in semi-eternal tides, meaning 2 high tides and 2 low tides each lunar day. But other regions, like parts of the Gulf of Mexico or the coast of Southeast Asia, experience diurnal tides, just 1 high and 1 low tide per day. In some areas, see mixed semi-diurnal tides, with 1 stronger and 1 weaker tide each cycle. The reasons are many: local seafloor topography, coastline shape, latitude, ocean currents, all conspiring to make the tide a unique experience in every location. And yet, despite this complexity, the moon remains the dominant force. Its presence shapes not just the ocean surface, but the lives and behaviors of countless organisms in marine biology. There's a term, tidal rhythm. Many coastal creatures have evolved to move, feed, reproduce, and hide in sync with the tides. Crabs retreat into their burrows as water recedes. Fish, like the grunion, use high tides to lay their eggs far up on the sand. Mussels clamp shut during low tide and reopen when submerged. These rhythms are so deeply wired into biology that they often persist even in controlled laboratory settings, as if the body remembers the tide even when the water is gone. And humans, too, have long known this rhythm. Ancient coastal communities built calendars based on the tide's timing. Early mariners learned to read the signs in moonlight and shoreline. Farmers in river deltas planted and harvested with the tidal flood. Fishermen timed their nets to the turning of the tide in Japan. The practice of USHIO-DOKI, or tide time, still guides traditional fishing villages. In parts of the Pacific Islands, knowledge of lunar phases and tidal flow is passed down through generations as part of navigational lore. The tide is not just a force, it's a clock, a teacher, a presence. And even today, with all our satellites and sensors, tide charts remain one of the most reliable forecasts on Earth. They do not surprise. They do not shift with politics or economies. They move with the moon. But tides are not only a vertical motion, they're also horizontal. As water rises, it flows inland. As it falls, it flows back. These tidal currents move vast amounts of water laterally along the coastlines, estuaries, and between islands, in narrow channels and inlets. These currents can become swift and dangerous, but also vital. They oxygenate coastal waters, transport nutrients, and influence the migration of marine species. They shape sandbanks, carve out channels, and sustain the delicate balance of coastal ecosystems. In some places, like the Mini Strait in Wales or the Naruto Strait in Japan, tidal currents are so powerful they create visible whirlpools, natural spirals of water pulled into dance by the moon's patient hand. In all of this, the bulges, the currents, the biology, the cultural memory comes from a force that began long ago, and a giant impact between Earth and a Mars-sized body likely formed the moon. Born of violence, now governs calm. And should the moon disappear, pulled from orbit by some cosmic accident, the tides would not vanish entirely. The sun also exerts a gravitational pull on Earth's oceans, so it's weaker than the moon's, but the tides would be lower, flatter, and the rhythm of life along coasts would change profoundly. The absence of the moon would be written in the stillness of bays, the confusion of spawning grounds, the silence of shoreline life that no longer knows when to move. But the moon is not leaving us, anytime soon. Its orbit is stable for the foreseeable future. Its light still traces silver paths across the water. Its gravity still tugs at the sea dot, so the tides will continue. And somewhere, right now, a wave is rolling ashore. Not a wave of wind, but a wave of the moon's making it creeps gently across. Sand kisses stone, fills the lungs of tidal marshes, stirs the bells of jellyfish, brushes against a barnacle shell, and withdraws as if the ocean were breathing through the moon. It's not loud, it's not fast, it is simply there. And in that constancy, we find peace. Somewhere along the western shores of a forgotten coastline, the tide begins its slow retreat. Seaweed left behind glistens in the morning light. Tiny tide pools emerge, scattered like dim mirrors on the sand, holding miniature worlds of crabs, anemones, and darting fish, all shaped by the clockwork pull of the moon. But beyond the daily ebb and flow, tides play a more profound and ancient role, one that quietly influences the very shape and geography of Earth. Over millions of years, tidal forces have subtly sculpted our planet. They've carved estuaries where rivers meet the sea, smoothed the edges of continents, and hollowed out channels and deltas. They have created fertile coastal plains, places like the Nile Delta, the Sundarbans, and the Thames estuary that teem with life and sustain agriculture and trade. These landscapes are not static. Tides shift sediments, rearrange coastlines, and build or erode land with astonishing patience. A single tide may move only a thin layer of sand, but across millennia, the effect is transformative. Coastal wetlands, salt marshes, mudflats, all of them are born of this daily motion. Tides are also the silent architects of many of Earth's most productive ecosystems, where fresh water meets the sea. A unique blend of salinity and nutrients occurs. These brackish waters form the basis for life-rich estuaries, places that support more biomass per square meter than even tropical rainforests. Here, the rise and fall of the sea becomes a rhythm for survival. Juvenile fish find safety in tidal creeks. Birds time their feeding with the lowering of the waterline. Grasses and mangroves anchor sediment with their roots, buffering storms and filtering pollution. This coastal choreography, shaped by the moon, supports an incredible diversity of life and has quietly helped sustain human civilization for tens of thousands of years. But tides influence not only the land and the life it harbors, they also interact with deep ocean processes, sometimes in ways we can't see far from the shore. In the open ocean, tides generate internal waves, slow-moving underwater ripples that travel along the boundaries of water layers with different densities. These waves, though invisible from the surface, can stretch for hundreds of kilometers and reach heights taller than skyscrapers. They stirred the deep ocean, driving the vertical mixing of water, and with it, the movement of nutrients, carbon, and heat. This deep stirring plays a subtle but vital role in global climate. It helps regulate the temperature of the ocean, distributes dissolved gases like oxygen and carbon dioxide, and supports the biological pump that draws carbon from the atmosphere and locks it in the deep sea for centuries. Without this mixing, the ocean would become stratified, with oxygen-starved depths and sluggish circulation. But with tides, the system breathes. This is one of the moon's lesser-known contributions to life on Earth, a role not only as a shepherd of the shore, but as a silent regulator of planetary health. And yet, despite this delicate balance, our world is changing. As the climate warms, polar ice melts, and ocean temperatures rise. These changes are beginning to shift tidal patterns, not because the moon has changed, but because the shape and density of Earth's oceans are evolving. Warmer water expands, raising sea levels. Melting glaciers alter coastlines and affect the gravitational balance between land and sea. As this happens, tide levels may rise in some places and fall in others. New tidal wetlands may emerge, while others may be lost beneath rising waves. Even the way tides interact with wind and storm surges is shifting. In coastal cities like New York, Miami, and Jakarta, tidal flooding is becoming more common not only during storms, but during routine high tides. These sunny day floods are quiet warnings of a changing equilibrium. As the moon continues its slow, eternal pull, the water it moves is growing warmer, deeper, and less predictable. But not all is lost. Some coastal ecosystems are remarkably resilient. Mangrove forests, salt marshes, coral reefs can buffer tidal energy and adapt to rising seas if given space and protection. Some human communities are learning from traditional knowledge, building with rather than against the tide, floating houses, elevated walkways, and adaptive agriculture that respects the rhythms of water. And there's a growing recognition that tidal energy, once a force to be feared or avoided, may be a key part of our future. Unlike wind and sunlight, tides are not weather dependent. They are predictable centuries in advance. In places like Scotland, South Korea, and Canada, underwater turbines now quietly spin with the turning tide, converting motion into electricity. It's not without challenges: maintenance, marine life impact, energy cost. But the idea that the moon might one day help power our cities is no longer poetic speculation. It's a technological possibility. This, too, is part of the moon's story, a story that reaches from ancient myth to modern engineering. For as long as humans have looked at the sea, we've felt the pull of something greater. Early seafarers noticed that tides seemed to match the moon's cycle. Farmers tracked planting seasons by the tides. Fishermen tied their hopes to the lunar calendar. Poets wrote of longing in the rising tide, and scientists measured its exacting schedule. We built bridges, canals, and ports around its timing. We named months after its phases. We told stories of deities who ruled the water with a glance. And even as we launched rockets into space, we did so from coasts shaped by tides, under the very moon that taught us how to measure time. Today, satellites circle overhead, precisely tracking sea level and tide height. The supercomputers simulate tidal flow across the globe. Our understanding is deeper, more precise, but not less wondrous, because even now, with all our instruments and models, the tide retains its mystery. It is still that thing which comes and goes and comes again. It asks no permission. It needs no explanation. It simply continues, as old as the earth itself and as gentle as sleep. A person walking along the shore may not notice the exact physics. They may not think about gravity or celestial mechanics or resonance and flow. They may not know that the water brushing their feet once rode a lunar wave across the ocean basin, but they feel it. They feel the pull, not as a scientist or sailor or philosopher, but as a body made mostly of water, listening to a rhythm that was always there, because that's what tides are, a lullaby sung by the moon. As dawn gives way to the quiet heat of afternoon, a boat rests gently in the shallow waters of a tidal inlet. The anchor rope, once taut, now slackens as the tide flows out once more. Below the hull, barnacles and oyster shells cling to submerged stones. These daily changes in water level, gentle for some, violent for others, tell a tale not just of gravity and motion, but of time itself. Time as measured by the moon's shadow on the sea. The concept of timekeeping owes much to the moon's influence over tides. Long before humans tracked minutes and hours with gears and springs, they looked to the sky and sea to understand the passage of days. Tides offered a natural metronome, predictable, recurring, tied to the lunar cycle. Ancient civilizations, especially those along the coast, learned to anticipate the sea's movement. In parts of Mesopotamia, the people of your tracked the moon's phases to plan agricultural rituals, including the flooding of canals and the salting of crops. In ancient China, early astronomers created water clocks calibrated with tidal charts, aligning maritime calendars with lunar cycles. The Greeks and Romans used the tides to time their harbor entrances in the Bay of Fundy. The Micmac observed the world's highest tides and passed their knowledge through oral storytelling, describing the living force of the sea's breath. Polynesian navigators, sailing vast stretches of open water, used tidal currents and swell patterns, guided by the moon's pull, to locate distant islands with uncanny precision. Tides, in many ways, are the moon's signature upon Earth's temporal memory. This lunar rhythm, though predictable, is not perfectly consistent. There are 2 high tides and 2 low tides per day, but they do not occur exactly every 12 hours. Rather, the tidal cycle lags behind the solar day by about 50 minutes. That's because the moon moves in its orbit as Earth rotates, creating a shifting alignment each day. This small delay accumulates over weeks. It causes the highest and lowest tides, known as spring tides, to align with full and new moons when the sun and moon's gravitational forces combine. At quarter moons, the tides weaken slightly, producing neap tides with less pronounced highs and lows. These rhythms overlay atop each other, creating a complex tapestry of motion that depends not just on the moon, but on the geography of the coastline, the depth of the sea, and the contours of the ocean floor. In some places, like the Gulf of Mexico, tides may be minimal, their motion dampened by geography. In others, like the English Channel, to become fierce and dangerous, capable of pulling massive currents through narrow straits. Even within a single region, the shape of a harbor or bay can dramatically amplify or diminish tidal effects. This is where resonance, the same principle behind a swinging pendulum, comes into play. If the natural oscillation of a body of water aligns with the timing of the incoming tide, the tidal range can increase dramatically. It's like pushing a child on a swing at exactly the right moment. Each nudge builds upon the last, creating large, powerful surges. This is what happens in places like the Bay of Fundy, where the tidal wave resonates with the bay's length, producing tides of up to 16 meters, enough to hide or expose vast stretches of land in a matter of hours. These unique tidal hotspots become ecological and cultural centers. In the Bay of Mont Saint-Michel in France, monks once timed their prayers to the sound of rushing tides echoing off stone abbey walls. In South Korea, the tidal festival celebrates the miracle sea road that appears during extreme low tide, a temporary causeway connecting to islands. In Venice, the delicate balance between sea and city remains a dance between stone, salt water, and the moon. But while the tides shape Earth, Earth also shapes the moon albeit more slowly. The tidal pull exerted by Earth creates a slight bulge in the moon's orbit, gradually pushing it away from us at a rate of about 3.8 centimeters per year. This may seem tiny, but over millions of years, it adds up. When dinosaurs roamed the planet, the moon was much closer, and tides were likely stronger and faster. As the moon recedes, Earth's rotation also slows. Days become longer by fractions of a second each century. In the distant past, a day may have lasted only 22 hours. In the far future, it might stretch to 25 or more. This planetary balancing act, a trade of momentum between Earth and Moon, is governed entirely by tidal forces. It's a cosmic exchange that mirrors our own biological clocks inside the human body. Many rhythms echo those of the tide. The circadian rhythm, our internal 24-hour cycle, responds mostly to light, but in coastal communities, ancestral patterns show signs of circadian and circadian entrainment, ancient biological echoes of living with the sea. Some marine animals still follow these patterns rigidly. Grunion fish, for example, time their spawning precisely with the highest tides of the full moon. Horseshoe crabs swarm beaches in a tidal synchrony that has remained unchanged for millions of years. Even coral reefs, hundreds of meters below the surface, time their mass spawning with the moon's phases, a synchrony so perfect that satellite images can detect the plumes of life released into the sea. These life cycles, tuned by the tides, reflect the moon's role not just in physics, but in biology. As our understanding of tides has grown more precise, we've begun to see their influence in unexpected places. Tidal forces have been detected in the shifting crust of the Earth, subtle flexes in tectonic plates that may trigger or suppress earthquakes, in some high-precision instruments, like atomic clocks and gravitational wave detectors. Tidal strain must be accounted for to maintain accuracy. Tides even affect time itself. According to Einstein's general relativity, gravity can bend time, an effect known as gravitational time dilation. Where gravity is stronger, time flows slightly slower. So as the moon pulls water upward during high tide, it changes the local gravitational field, infinitesimally altering the flow of time. It's a difference far too small to affect human life, but one that speaks to the astonishing interconnectedness of the cosmos. From the lapping of waves at our feet to the ticking of time itself, the moon's influence is subtle, quiet, and ever-present. And yet, for all this complexity, there is something deeply comforting about the tide. It is ancient. Yes, it is powerful, certainly, but it is also gentle. It does not arrive with the chaos of storms or the violence of fire. It simply comes and goes, predictable, soothing, reassuring, in an ever-changing world, with its surges of noise and information, its uncertainty and acceleration. The tide remains a rare constant. It whispers, not shouts. It reminds us to slow down, to breathe, to wait, because some things, the most essential things, move not in haste, but in rhythm. As one tide leaves, another arrives, and beneath the moon's gaze, the earth continues to turn. Even as we drift farther into this deep understanding of how the moon pulls at the oceans, another layer of complexity begins to surface, a layer shaped not by water alone, but by air, land, and the sheer physics of planetary motion. If the moon is the brush, then Earth is the canvas upon which it paints the tides. Let us begin with the idea of amphitronic points, silent centers in the oceans around which tides rotate. Unlike the simple notion of water rising and falling in a synchronized rhythm across the globe, the reality is that tides rotate like a giant pinwheel. Around these amphitronic points, tidal waves sweep in circular paths, their motion dictated by Earth's rotation, the shape of ocean basins, and the Coriolis effect. Picture it. Somewhere far out in the ocean, there's a spot where the tide doesn't rise or fall at all. Round it, the sea heaves and sighs, cycling every 12 hours and 25 minutes. These points are not fixed, and they're not marked on any map, but they shape everything from coastal ecosystems to shipping routes. Europe, for example, is bordered by the North Sea, where tides sweep counterclockwise around an amphidromic point off the eastern coast of the UK. In the South Pacific, the tides spin the opposite direction around their central node. This amphidromic dance ensures that not every coastline experiences the same kind of tide at the same time, even if they're on the same latitude or directly across from one another. This is why the timing of high tide in one port may be completely out of sync with another, even one just a few hundred kilometers away. It's a reminder that Earth's oceans, though connected, respond to a web of invisible forces. The moon's pull may be the metronome, but the beat is shaped by the shape of the oceans themselves. And then there is the wind. Tidal movements often mix with wind-driven surface currents, creating patterns that can deceive even experienced mariners. In some regions, strong winds can hold back tidal surges, delaying high tide. In others, they accelerate the flood, forcing coastal communities to prepare for higher than expected levels. Storm surges, the dangerous swelling of ocean water. During cyclones and hurricanes, often combine tidal forces with wind pressure, creating a deadly synergy. In low-lying countries like Bangladesh and parts of the Netherlands, the difference between a manageable tide and catastrophic flooding can be just a few centimeters, the height of a curb, width of a doorstep. Thus, understanding tides isn't just academic, it's vital for survival. And that understanding has come a long way. Early attempts to predict tides relied on observation. Priests and sailors kept records of tide times, sometimes carving notches into harbor walls or marking them in almanacs. By the 17th century, Sir Isaac Newton had mathematically described the relationship between gravity and tidal forces, confirming that both the moon and the sun exerted influence over Earth's oceans. But Newton's work was only the beginning. The French mathematician Pierre-Simon Laplace expanded on the theory in the 18th century, developing a set of partial differential equations, now known as the Laplace tidal equations, that described how tides should behave in a rotating, fluid-covered planet. These equations were incredibly advanced for their time and laid the foundation for modern tidal modeling taught today. Satellites like TOPEX, Poseidon, and Jason 3 orbit Earth, bouncing radar signals off the ocean surface to measure sea level changes with centimeter accuracy. Supercomputers take these data and combine them with detailed maps of seafloor topography, wind data, lunar cycles to generate higher resolution tidal forecasts in major ports around the world. Harbor masters rely on these forecasts to determine when large container ships can safely enter or exit. For oil platforms, offshore wind farms, and coastal engineering projects, precise tidal predictions are not just helpful, they're essential. But even with all this precision, the tides remain wild in many ways. They are not beholden to us. They do not follow human time zones or obey borders. They do not respond to our convenience. And perhaps that's part of their charm, because as much as the moon controls the ocean still answers to the earth, to its shape, its spin, its storms, and its seasons. Tides vary, not just by day or month, but by year and decade. Oceanographic cycles, like the El Niño's Southern Oscillation, the Atlantic multi-decadal oscillation, and even global warming can influence long-term tidal patterns as polar ice melts. For example, the redistribution of water mass across the planet alters oceanic pressure and sea levels, which in turn affects tidal behavior. Even the melting of glaciers can subtly shift Earth's center of mass, changing how the moon's gravity pulls at the sea. In this way, the tides become not only a result of cosmic rhythm, but a reflection of our planet's shifting climate. And yet, throughout these changes, the moon continues its quiet journey, orbiting Earth every 27.3 days. its face eternally turned toward us. This synchronous rotation, where the moon rotates on its axis at the same rate it orbits Earth, means we always see the same side. The far side, the so-called dark side of the moon, remained unseen until the space age, but even that side, hidden from our view, plays its part in pulling Earth's oceans. It's one of nature's most perfect synchronizations, born from the same tidal forces. Observe here below. As the moon raised tides on the early Earth, the drag slowed our planet's spin and transferred energy to the moon, pushing it outward. Over billions of years, the moon migrated away from Earth, reaching a distance of about 384,400 kilometers today, and still, that ancient pull continues. The moon's gravitational force is about 1/6000th the strength of Earth's. Yet, its impact on our oceans is immeasurable. The ocean, fluid, restless, and vast, responds in kind, lifting up not just its surface, but our awareness of connection between Earth and moon, between sky and sea, between science and story, because the science of tides is also the science of poetry. Sailors once spoke of the tide as a living creature. Poets used its rhythm as metaphor for love, death, and rebirth. Entire spiritual systems were shaped around its pulse. The tide doesn't just carry boats, it carries meaning, and that meaning continues to ripple outward. In classrooms, children learn about the moon, not just as a light in the sky, but as a sculptor of shorelines. In observatories, astronomers use lunar data to model exoplanets and the tidal forces they may experience. On beaches, families time their vacations with the tide tables posted in tourist shops. High tide for swimming, low tide for exploring. Tide pools, those tiny worlds in rocky cradles, remind us that even in the smallest puddles, the cosmos has a hand. There, amid the kelp and sea anemones, gravity bends the water's edge. Tiny crabs adjust their pace. Snails cling to rocks, waiting. The moon, so far away, touches them just as it touches the greatest ocean trench. And so it continues, with every rise, with every fall. A force not heard, but felt. Not seen, but known. Not feared, but respected. The tides shape us, guide us, humble. U.S. They are Earth's slowest breath. And in their rhythm, we find peace. Beneath the surface, tides are far more than waves that lap at the shore. They are deep in subtle movements, slow undercurrents, shifting water masses from one hemisphere to another. In the deep ocean, tidal forces stir nutrients, oxygenate marine layers, and quietly govern the lives of countless organisms. To a casual observer, the ocean may seem calm during a full moon, but beneath, entire ecosystems feel its pull. Microscopic plankton, for instance, migrate vertically in rhythm with tidal cycles. This phenomenon, called diel vertical migration, is the largest synchronized movement of biomass on Earth. Billions of these tiny organisms rise toward the surface at dusk and descend again at dawn, guided not just by sunlight, but also by the rhythm of the tides, which control nutrient upwelling and predator behavior. These plankton feed small fish, which feed larger fish, which in turn support marine mammals, seabirds, and human fisheries. A gravitational pull that begins over 384,000 kilometers away ends up feeding whales and feeding families. The connection is invisible, but persistent. This underwater choreography also affects coral reefs. Corals are living animals, building vast limestone structures over centuries. Many coral species time their mass spawning events to coincide with tidal patterns and lunar phases. At precise moments, often during a specific phase of the moon, and at the slack tide between ebb and flow, entire reefs release clouds of eggs and sperm into the water, turning the sea into a slow-motion snowstorm of life. Why such timing? Because it works. The stillness of slack tide helps ensure these reproductive cells stay suspended long enough to fertilize. The moon sets the calendar. The tide opens the window. And the future of the reef unfolds in silence. In tidal estuaries, where rivers meet the sea, the relationship between tides and life is even more immediate. Estuaries are rich and productive, but only because the tides flush them twice a day, washing in seawater, stirring up nutrients, and helping juvenile fish find their way to safer waters. Without the tide, estuaries would stagnate. Life would choke. The moon sustains them without ever touching them. Meanwhile, in the human world, people have used the tides as a source of power for centuries. As early as the Middle Ages, tide mills were built along the coasts of France and England. These mills captured water during high tide in a reservoir. When the tide receded, the stored water was released to turn a wheel, grinding grain into flour. It was gravity-powered agriculture, a renewable energy source long before we named it that today. We are returning to this old idea with new technology. Tidal energy projects, from underwater turbines to floating barrages, are being explored around the world. Like solar and wind, which can be intermittent, tidal energy is predictable to the minute. The moon may move slowly, but it moves reliably. And yet, tides are more than just mechanical opportunities. They are woven into culture, religion, and myth in Maori traditions. The moon, called Marama, is viewed as a guiding force for planting, fishing, and travel. Elders passed down knowledge of the moon's phases and their impact on the tides long before telescopes or textbooks. In the Maldives, ancient mariners used tidal markers carved into stone to predict safe harbor conditions. In the Philippines, local fishermen have tuned their nets, not to the clock, but to the sea, sensing by habit when the tides would shift. These aren't just stories, they are empirical truths, tested by survival. The tide waits for no one, but those who listen can move with it. Modern cities, too, live by the tide, whether they know it or not. In Venice, Italy, the city's fate is tied to the Adriatic Sea. High tides, known locally as acqua alta, flood the plazas, turning stone walkways into silent lagoons. The city's elaborate moats project, a system of retractable barriers, now rises during high tides to protect the fragile architecture. There, the moon has become a guest that must be anticipated, prepared for, and at times blocked. In London, the Thames Barrier stands guard against storm surges and tidal floods. In New York, new waterfront developments consider tide levels, storm tide projections, and sea level rise as part of their foundational design. Tides are no longer just something to watch from a pier. They are a design variable, an engineering challenge, and sometimes a threat. As sea levels rise globally, the tides carry more water onto coastal land. Places that once flooded once a year now flood monthly. In some Pacific Island nations, traditional wells are becoming brackish. Cemeteries are being relocated. The tides, once a benign reminder of cosmic order, are now rising symbols of disruption. Still, there is something ancient and unshakable about them. Standing on a quiet beach, watching the tide creep in over wet sand, it's hard not to feel time slow down. The moon above, so small to the eye, exerts such influence. Every grain of sand that shifts, every crab that burrows deeper, every gold that lifts in the breeze, they all respond, somehow, to that pale, cratered satellite. It reminds us that we are not separate from nature's rhythms. We are inside them. Our blood contains salt. Our bodies are mostly water, and we, too, are pulled. Astronauts on the International Space Station have spoken of how the sight of Earth wrapped in oceans, spinning beneath a single moon, evokes a feeling of unity, of belonging. They can see the tides from space. The movement is slight, but visible. The moon does not favor one nation over another. Its pull is even. Its rhythm is fair. It reminds us of a kind of balance we rarely achieve on our own. And so the tides roll on, up and down, in and out, again and again. A gravitational handshake between celestial bodies felt across bays, cliffs, mangroves, and mudflats. A force that shapes the migrations of whales and the work schedules of dock workers. That tells the oyster when to close, the seaweed when to sway, the dolphin when to leap. The moon controls the ocean, but not with a shout, with a whisper. Its influence is so quiet, so continuous, that we often forget it's there. But the ocean does not forget. It never has. And now, in an age of satellites, sensors, and supercomputers, we still find ourselves checking tide tables, scheduling ship launches, watching the swell, and reading the water, because in the end, for all our science, for all our infrastructure and data, we remain creatures of the tide. We walk beaches that the moon designs. We sail seas shaped by its gravity. We write poems in its rhythm, and we fall asleep to the hush of its return. It is the heartbeat beneath the ocean, the breath between waves, the silent motion that cradles life. Not just marine life, but all life, all life. Elsewhere in the solar system, there are other moons orbiting other planets, and many of them also influence tides, though not of water. On Jupiter's volcanic moon, Io, gravitational tugs from both Jupiter and its neighboring moons stretch and compress the moon's crust. This friction heats Io's interior, giving rise to the most volcanically active body in the solar system. There are no oceans there, but the principle is familiar. Tidal forces as a source of energy. On Saturn's moon, Enceladus, beneath an icy shell, a hidden ocean sloshes and churns due to similar tidal stresses. Geysers erupt from cracks at its south pole, spraying water vapor into space. That same material contributes to Saturn's earring and may hold clues to habitability. Tides, then, are not just Earth's affair. They are universal, a language of motion spoken across the cosmos, wherever gravity binds to bodies in orbit. Back on Earth, scientists now use tidal data to study much more than just beach conditions. Tides are helping to model climate change, track glacier melt, and even detect subtle changes in Earth's rotation. The moon's steady influence offers a kind of cosmic metronome, a reference point against which to measure the planet's smallest shifts. For example, the tidal friction created as the moon pulls on Earth's oceans acts like a brake on our planet's rotation. Every year, Earth's spin slows down ever so slightly, about 1.7 milliseconds per century. Because of this tugging, over hundreds of millions of years, this effect has accumulated. Ancient corals, which lay down daily growth rings, show evidence that there were more days in a year long ago, around 400 days, some 400 million years ago. Earth was spinning faster, the moon was closer, and the tides were different. This slow exchange of energy between Earth and moon is part of what's called tidal locking. Earth's rotation slows down, and the moon gradually moves farther away, about 3.8 centimeters per year. Ask the rate at which your fingernails grow. But given enough time, it reshapes the relationship between planet and satellite. One day, far in the future, Earth may become tidally locked to the moon, just as the moon is now locked to Earth, always showing the same face. In that future, Earth days and lunar months would match. The moon would hang unmoving in the sky, and tides, as we know them, might cease to flow. But that's billions of years away. For now, the moon remains a patient conductor of tides, turning the ocean surface into a slow, ceaseless symphony. And we are learning how to read that score in more detail than ever before. Today's satellite calorimetry systems can measure sea surface heights down to the centimeter. Caloritographers can model tidal flows across the globe, mapping where they speed up in narrow straits and slow in wide bays. Engineers use this data to plan tidal power arrays, while ecologists rely on it to understand where certain fish will spawn or where sediment will accumulate. But the moon's influence isn't limited to the sea alone. Recent studies have shown that atmospheric tides, subtle shifts in air pressure driven by lunar gravity, also occur. They are weaker than solar-induced atmospheric tides, but measurable. These tiny pulses affect wind patterns and cloud formation in ways we're just beginning to understand. Even groundwater feels the moon's tug. Deep in aquifers, buried beneath layers of rock and soil, the pressure within wells can rise and fall slightly with the moon's phase. This is not myth, it's measured, documented, and used in hydrological studies around the world. Then there's the human side. In some traditions, the moon and its tidal influence are tied to human health, while folklore about the full moon causing madness or sleep disruption remains mostly anecdotal. Researchers continue to study whether lunar cycles affect melatonin production or sleep architecture. Some data suggest that people may sleep slightly less deeply during the full moon, though the effects are subtle and still debated. What's certain is that for millennia, human culture has turned its gaze upward and found rhythm in the moon. From agricultural calendars to seafaring charts, from poetry to practical engineering, the moon's gravitational gift has shaped not only our oceans, but our civilization. In ancient Mesopotamia, lunar cycles governed the planting season and temple rituals. In Polynesia, navigators used the moon's position and tides to cross vast stretches of open ocean. In medieval Europe, monasteries rang their bells according to tidal hours, marking not just time, but flow. And still today, in quiet coastal towns and busy harbors alike, the tide dictates daily life. There are places where you can hear the tide coming, like the Bay of Fundy in Canada, home to the highest tides on Earth. As water surges in, it flows upriver in a visible wall called a tidal bore, pushing against the current and roaring like thunder. There are places where the tide uncovers ancient footprints, as in the Severn Estuary in the UK, revealing ghost tracks left by people thousands of years ago. And there are places where the tide decides whether you'll reach home, such as Mont Saint-Michel in France, an island monastery once only accessible during low tide. In all these places, the moon's invisible hand draws lines between land and sea, between motion and stillness, between past and present. Even animals inland are not immune to this lunar choreography. Amphibians, such as toads, have been observed timing their spawning to tidal cycles, even when far from the coast. Birds, nesting in tidal marches, align their breeding to avoid the spring tides that might flood their eggs. And in the human heart, whether scientific or poetic, the moon continues to shape longing, routine, and imagination. In space, astronauts still train using tide-based schedules, simulating Earth-Moon-Earth communications during missions. The delay is only a few seconds, but it reminds us of the real distances involved and of how small forces like lunar tides carry out enormous tasks silently. As we look ahead toward future lunar bases, perhaps even human settlements on the moon, we'll be living closer to the source of these tidal rhythms than ever before. The moon that once merely pulled on us from afar may become our new frontier, offering a perspective both intimate and humbling. Back on Earth, the tide comes in, then goes out. A grandmother watching from her porch might say the sea is breathing, and perhaps she's right, because even as we develop more precise instruments, even as we refine our data and upgrade our models, the experience of the tide remains unchanged. It's something you feel, not in your mind, but in your chest. A pull, a quiet shift, a rhythm older than language. Stand by the water's edge. You'll see it, the sea creeping closer, receding again, rearranging driftwood and dreams alike. The moon does not need permission. It pulls, and the earth answers. In the quiet hours before dawn, when the world is still and the sky turns a soft faded gray. Something remarkable is happening across the coastlines of the planet. Unseen by most and heard only faintly, the ocean begins to stir. Not in anger or urgency, but in a deep, patient motion that has never once broken its rhythm. That's the tide, the ceaseless breath of the Earth's ocean, drawn by the moon's invisible hand. To understand this motion is to understand one of the most delicate and consistent interactions in the solar system. The moon, smaller than Earth by a wide margin and with no light of its own, quietly exerts influence over the entire mass of Earth's oceans. And it does this not with brute force, but with the elegance of gravitational subtlety, through a force so familiar, so constant, that we barely notice it yet. If it were to stop, even for a moment, the consequences would ripple through every living system on Earth. The oceans rely on the moon for motion, but that motion supports life in ways that go far beyond the beach. Tides are not simply the back and forth wash of waves on a shoreline. They are the deep, regular cycling of vast masses of seawater, moving nutrients, redistributing energy, shaping coastlines, and dictating ecological patterns from microscopic plankton to migrating whales. Take plankton, for example. These tiny organisms, many of them no larger than a dust mote, are the base of the marine food web. Their movement is partially dictated by tides. In estuaries and coastal zones, tidal currents stir nutrient-rich waters, bringing life-sustaining elements up from the deep and allowing phytoplankton to bloom. These blooms, in turn, feed small fish, which feed larger fish, which sustain entire ecosystems in the open sea. Tidal currents help regulate the ocean's conveyor belt, the thermaline circulation that distributes heat and salinity across the planet. Without it, tropical waters would remain hot and stagnant, while polar seas would grow colder and more isolated. Tidal action plays a part in stirring these massive flows, especially in regions like the Southern Ocean and mid-ocean ridges, where tides interact with underwater topography. But tides aren't just about water, so they affect sediment too. Along the world's coasts, from mangrove forest to tidal flats, the moon controls the distribution of fine silt and sand. These sediments become the foundation for nurseries of marine life, crabs, oysters, clams, and a multitude of other intertidal creatures rely on the exposure and flooding of these zones to survive. Entire bird migrations are timed to tidal cycles, as are the hunting habits of predators that stalk the shore. And still, beyond all of this, tides are silent architects. They shape the land, the sculpting of sea caves, the carving of arches, the smoothing of stones, all are products of centuries of lunar-led erosion. Even the deepest submarine canyons owe part of their formation to ancient tidal currents channeled through narrow straits over millennia, and the moon, unwavering in its orbit, continues to drive it all. We often picture gravity as a simple force, a pull downward, but in truth, it's a dance, especially between Earth and Moon. The moon's gravitational pull on the near side of Earth draws the ocean toward it, creating what we call a high tide. But on the far side of Earth, the ocean also bulges, not because the moon pulls it, but because the moon pulls Earth itself slightly away from that water, leaving another high tide in its wake. So there are always two bulges, two high tides at once on opposite sides of the planet. As Earth rotates through these bulges, every coastline experiences a rise and fall in sea level, usually twice per day. But this timing is not fixed by the clock. The moon takes about 24 hours. It's 50 minutes to return to the same position in the sky, meaning tides occur roughly 50 minutes later each day. That's why, if you go to the same beach every morning at the same time, you'll notice the tide has changed. It has slipped out of sync with human timekeeping, not out of disorder, but because it follows lunar time. This lunar time is ancient. It predates humanity, predates most life on Earth, Marine organisms evolved in rhythm with these tides. Some have internal clocks so precisely tuned to them that they can detect the moon's gravitational phase, even in laboratory darkness. Corals release their spawn with lunar regularity. Some worms bury or rise in time with the spring and neap cycles. Even invertebrates without eyes or brains seem to know the moon. And long before digital watches or mechanical clocks, humans too knew the moon's schedule better than they knew the stars. They lived by it. In fishing villages, tide tables were passed down through generations. In temple records from ancient China and India, astronomers tracked lunar cycles, not for astrology, but to predict floods. In the Pacific Islands, navigators plotted sea routes based on tidal drift. And in Britain, where rivers like the Thames and Severn meet the sea, entire communities were built to withstand or utilize the incoming board tides that race inland with surprising power. Even in modern cities, Tokyo, New York, Karachi, tides influence urban infrastructure. Seawalls, sewage systems, and shipping schedules are all built on tidal expectations. And yet, for all this, most of us barely notice. We stand on the shore, the tide rises at our feet, and we treat it as background. But to understand the tide is to be reminded that we are connected deeply, physically, to something far above. And the moon is not alone. The sun too influences tides, though its pull is weaker due to the greater distance. When the sun and moon align during new and full moons, their gravitational forces combine to create spring tides, higher highs and lower lows. When they are at right angles during quarter moons, they produce neap tides, less extreme variations. This interplay gives Earth's tides a graceful complexity, not just a steady rise and fall, but a layered rhythm of long and short beats. These beats echo through the ocean basins, bouncing off continental shelves, colliding and merging in ways that form amphidromic points, places where tides cancel out completely and the sea barely moves. Around these points, the tides rotate, setting up patterns unique to every coastline. It's as if every bay, inlet, and estuary has its own musical score, all conducted by the moon, arranged with the sun's harmony, and shaped by the contours of the earth. And like music, these patterns affect us emotionally as well as practically. For some, tides bring nostalgia, memories of walking barefoot along tidal pools or watching a pier disappear beneath rising water. For others, they represent a kind of peace. The tide will come, and then it will go. There is nothing to be done, no intervention required. It reminds us that some forces are simply to be observed. Even in space, future missions to Mars and beyond may seek tidal evidence. Martian moon like Phobos, spiraling slowly inward, might one day shatter from tidal stress. Frozen exoplanets around distant stars may harbor subsurface oceans heated by the gravitational tug of a nearby body. In these cases, the same fundamental physics applies. A tug, a bulge, a movement, gravity signature. So tonight, as the moon climbs once more into the sky, the tide moves silently toward the land. It is worth pausing, not to act, not to intervene, but to remember that above us, far beyond the rooftops and city lights, an ancient rhythm continues. One that connects water and stone, salt and wind, creatures and calendars. It is the moon's rhythm, and it never misses a beat.